Hi, everyone. Welcome to our first lecture on machine learning. So this is a different lecture than what we've seen before. This isn't a coding lecture. This is actually going to be a conceptual and, yes, a little bit mathematical lecture on what machine learning really is and how it works. And I know this is Pick 16A, it's Python programming, it's not a math class. But I do think that as we start thinking about how to use Python to do machine learning, that we have a firm conceptual understanding of what it is we're doing. And that's what we're going to work on today. So this lecture is a conceptual overview of machine learning. And there is a big message that I want you to always keep in mind as we are working on machine learning and as we are continuing with this lecture and into the coming lectures. And the big message is that machine learning is function approximation. And at its core, that's all that machine learning is, okay? So in order to illustrate this point, I'm going to draw a picture that has a few different parts, and we're not going to be familiar with all the parts immediately, but I'm going to come back to the parts and give you the definitions so that we can see them in action. So if you don't understand everything that's going on here, that's okay. So here are the parts. First, we have some predictor variables. So the predictor variables, which I'll call x, are the data that we have access to in order to make our predictions. We additionally have, usually just one, target variable, and that is the thing that we are trying to predict. Now, what we usually imagine mathematically is that there's some kind of true relationship between the predictors and the target. And we unfortunately don't know what the true relationship is. What we have instead is some data, and that data is assumed to be pretty close to the true relationship. So here I have some data points that I can use. I imagine that I've measured these or collected these in some way. Now, what we want to do is to find a function that is close to the true relationship. And we'll see how to do this as we go through the course. Really, that's a lot of what applied machine learning is finding this function. But let's just draw a function in here. So I'm going to draw a linear function, since I think many of you are familiar with linear regression or linear data fitting, as it's sometimes called. So here is a function between from the predictors x to the target space y. And this function, we try to have this function be somehow close to the data. And the way we measure closeness is often by some measure of what I'll call error or loss. Okay, so I'm going to just draw in here these little lines I'm drawing, these little red lines. These are the prediction errors. So if the function says, hey, I am expecting that based on the predictors, I'm expecting the target variable to have this value, then these little red lines tell you the difference between what the function says the value is expected to be and what the value actually is. So here's our fundamental picture. We have predictors, a target. There's a true function between them. That's what we want to approximate. We don't actually have access to the true function. We have access to some data. And we use a substitute, a fake model that we aim to be close to the true model in some way. And because we can't get to the true model, we aim for it to be close to the data we have some ability to access. So let's go into a little bit more detail now about what these components are. So I started with the predictors. So the predictors, which I called x, the predictors x are part of the data that I have gathered. These are information that the model, sorry, I'm just going to give that a little color, that the model will use to predict the target variables y. Okay, so my predictors x, they're in my data, I have access to them. Okay, my target variable y. Now, this is also part of the data when I am training the model. So later on, we are not going to let ourselves see the target variable y in the data. That's when we start testing the model. But when we're training the model, we have access to it. And this is what the model aims to predict. Okay, so this is what we want to be able to predict, and we do it using the predictor variables. Okay, so far we have ourselves predictor variables x and target variables y. So sorry, in case you're not sure here, these are the predictors, also called predictor variables. Okay, so now I want to just give a quick example here so that we can actually kind of think about predictor and target variables in action. So let's think about a few hypotheses that'll give us some concrete examples here. So here's a hypothesis. So suppose I'm considering whether or not a passenger survived on the Titanic wreck. So this is a very famous wreck of a boat, and there were some survivors, but not too many. And this is a kind of an odd example, but it's very common because this data set is available, and so you can train machine learning models using this way. So an example in this case might be we ask ourselves the question, is it the case that how rich you were predict whether you survived on the Titanic? And the answer is, you won't be surprised to find out, is yes. How rich you are does indeed predict whether you survived on the Titanic. Here's another one. So we can ask ourselves, does GDP predict average happiness in a country? So these are just two simple examples where we have a predictor variable, how rich you were, or GDP. So in I guess both of these are about how rich you are in some sense. And then that predictor variable is used to predict a target. So whether or not you survived on the Titanic. So that's a yes or no question. You can predict yes or no questions. Or you can also predict something that you might measure with a numerical score, like average happiness. Okay, so now moving on, we have two more parts of the function approximation story. So we've talked about the horizontal axis here, that's the predictors, and we've talked about the vertical axis, that's the target. So now I want to talk about this model, that's the blue line, and then the errors, those are the little red bars. So the model in a machine learning problem, technically speaking, it is a function So a function in the mathematical sense, I'll call it f for function, very exciting, that maps elements of the predictor variables to elements of the target variables. Okay, so this says, hey, give me some input that looks like the predictor variables. Give me a GDP, for example, and I'll spit you out an average happiness. And that's my prediction for what the average happiness is in this country. So this function maps the predictors to predictions of the target variables. Okay, so what this model does is it says, how does GDP predict happiness, for example? So here's a simple example. So sticking with the GDP example, okay, so we can ask ourselves, not just does GDP predict happiness, how does it predict happiness? So here's an example. Is GDP linearly related? So does the relationship between GDP and average happiness look like a line? So is GDP linearly related to average happiness? So this is the kind of question that specifying the model specifies, is what kind of relationship is it? So just as a quick picture here, so here is my target axis, here is my, or sorry, here's my predictor axis x, there's my target axis y. And then when I'm asking about the model, I say, well, maybe it's a linear model. Does it look like this? Or maybe it's some weird wavy model like that. So maybe it's a model like this instead. So when I ask about my model, I'm asking which of these functions will be better at predicting my target variable from my predictors? Which of those models do I want? Okay, now the next question is, what does it mean for one model to be better than the other one? How do I choose between those two options, the straight line and the squiggly line? And the answer is specified by what's called a loss function, which I'll call L, and I like to give it a little curly curly font here. So this is the loss function L. And the loss function L is a quantitative measure of how much error the model makes when we predict the target variable using the predictor variable. Okay, and specifically, this is what the loss function does is we use it to compare different models. Okay, so we can use this to ask ourselves, which model is better than another one? So let's look at a few examples here of this. So um, here's a few examples of loss functions that you might not necessarily think about in this technical way, but let's give it a shot. So the model, let's think about the Titanic. Let's give that its right color. Okay, so let's say that the model, and then let's measure quality, wrongly predicts that a passenger survived, for example, 11% of the time. So this is a measure of the quality of the model. Similarly, for the case of GDP, we could say something like this. The model is, let's say we're trying to measure or predict a numerical GDP score. Let's say it's off by 0.3 points on average on some scale that we would have to specify in its predictions. So these are both instances of loss functions, okay, loss functions. These tell us how good a specific model is or not good. So what we then want to do when we do machine learning, and I'm going back here to this fundamental diagram here, when we do machine learning, we want to find ourselves an example of a good blue line, a good model that minimizes the loss function, that makes few errors, or makes a small error on average, something like this, when it predicts the target functions. That's what we want to do. So mathematically, when we say that we want to find the best model, this is what we usually say when we want to do machine learning, quote unquote. Mathematically, what this looks like is the following math problem. Minimize the loss function. And what's the loss function a function of? Well, the loss function compares the predictions to the actual target variable values. So the predictions are the values of the function f on the predictor variables, and those are compared to the true values of the target variable y. And we want to minimize this across all choices of f. Remember, f is the model. We want to minimize this across all choices of f in some set m of possible models. Okay? So this is the fundamental math problem at the heart of machine learning. We want to minimize the loss function in the set of possible models. Okay, so there are a lot of problems that this can pose for us. So we can ask ourselves questions like, which predictors are the best predictors? Which loss functions are appropriate for the problem that we're looking at? Which set of models M is most appropriate for my data set? And then furthermore, for that matter, mathematically, how do I actually find the best model? How do I do this minimization problem? It's often computationally very difficult. So these are some of the core problems at the heart of machine learning. And we are going to look at not all of them, but some of them as we work together in our time studying this machine learning problem. So that is our lecture for today on the conceptual overview of what machine learning really is. And in the following lectures, we'll start looking at how to understand this theory and how to use Python to achieve machine learning tasks. Okay, stay tuned.